Today we're going to look at systems of differential equations of the form y prime equals a times y, where A is a diagonalizable matrix. So we're going to first consider those systems, y prime equals a times y. A is a constant matrix. And we're going to let V be an eigenvector of A with corresponding eigenvalue lambda, meaning that A times V is equal to lambda times V. Then we've seen in the past that a solution of y prime equals A times y is in fact e to the lambda t times our eigenvector V. Now, how do we know that? We know that dy dt in this case is equal to lambda e to the lambda t times v. But we also know that a times y is equal to a times e to the lambda t v. But e to the lambda t is a scalar, so we bring that out, and that's times av, and that's equal to e to the lambda t times lambda v. And so dy dt is in fact a times y in this case. So now what is the general solution then for an n by n matrix? Well, if A has a full set of eigenvectors, v1 through vn, with corresponding eigenvalues lambda 1 through lambda n, then we can write down a fundamental set of solutions, which is a set of n linearly independent solutions. Those solutions look like y1, which is equal to e to the lambda 1t v1, y2, which is e to the lambda 2t v2, all the way down to yn, which is equal to e to the lambda n t vn. And we know that those solutions form a fundamental set of solutions because they're linearly independent, and they're linearly independent because the eigenvectors v1 through vn are linearly independent. Now, essentially what we're saying is that if A has a full set of eigenvectors, then we can come up with this fundamental set of solutions. But the criteria for A to have a full set of eigenvectors is the same as saying that A is a diagonalizable matrix. Okay, so that's why in particular we're going to look at these diagonalizable systems. So let's look at what the general solution will look like. So y of t will be a linear combination of those basis functions. So that's c1 e to the lambda 1t plus, times v1 plus c2 e to the lambda 2t times v2, and then all the way down to cn e to the lambda nt times vn. Now what I'd like to do is essentially put this in matrix vector form. So I'm going to make a matrix, I'm going to call it P, and I'm going to multiply P times a vector. The vector is going to be c1 e to the lambda 1t, c2 e to the lambda 2t, all the way down to cn e to the lambda nt. And because of how matrix multiplication works, then P must be the matrix whose columns are the eigenvectors v1, v2, all the way down to vn. So this is just one way that we can write the general solution. We can write it as the matrix of eigenvectors times a column vector that has all of the exponentials with the eigenvalues times t in it. So you can see my question, what is really going on here? Okay, why is it that, that we can write our system this way? Well, let's go back to that idea that I said that A, in this case, is diagonalizable. Okay, so it has a full set of eigenvectors. That means that I can write it as P times D times P inverse, where D is a diagonal matrix whose entries are lambda 1, lambda 2, all the way through lambda n. Okay, so we can think about it as the matrix with lambda 1, lambda 2, all the way down to lambda n, and then zeros elsewhere. Well then, if that's the case, we can actually write our system that way. We can write it as y prime equals P D P inverse times y. Okay, I'm going to multiply both sides by P inverse. So I'm going to say this is P inverse y prime on one side, and then equal to P inverse D, P inverse P D P inverse y on the other side. So P inverse times P is going to be the identity, so that's going to kind of cancel there. And then, in fact, I'm going to write this as P inverse times y prime. I can do that because of the linearity of the derivative. And that equals D times P inverse y. I'm going to put parentheses around that. Oh, well, that means that I could think of this as being the system Z equals Z prime is equal to D times Z, where Z is equal to P inverse times y. Now, when you multiply a vector like y times an invertible matrix like P, what is really going on here is that you're doing a change of basis. So this is a change of basis. We're changing the basis of our problem from the standard basis to a basis of eigenvectors. Okay, in fact, when we wrote A as PD P inverse, like we did here, what we were doing was we were performing a change of basis. We were changing the basis from the standard basis to the basis of eigenvectors. Okay, and the linear transformation A is much simpler on this basis. So what we have here is that A is a simpler transformation on the basis of eigenvectors. It's simpler because now it's just a diagonal matrix. So what we have here is a series of problems that are fairly simple to write out. So since D is diagonal, what we have here is that z1 prime, z2 prime, all the way down to zn prime as a vector is actually equal to, that diagonal matrix has the eigenvalues, so lambda 1, lambda 1 z1. When we multiply D, the diagonal matrix, times z, we will get lambda 1 z1, lambda 2 z2, all the way down to lambda n zn. And so what we have is n differential equations that no longer depend on each other. And so in fact, we can write this as the solution, as z1, z2, all the way down to zn is equal to c1 e to the lambda 1 t, c2 e to the lambda 2 t, all the way down to cn e to the lambda nt. Okay, these are very simple exponential growth or decay differential equations to solve. Okay, so now we can write it that way. Another way that we can write this, another way to look at this, is we can think about it as z equals the diagonal matrix of, let me write this in a slightly different spot. We can think about it as z equals the diagonal matrix of e to the lambda 1 t, e to the lambda 2 t, through e to the lambda nt, times the vector c1, c2, all the way down to cn. We want to write it in matrix form. So what we've done is we've transformed this problem where we originally had y prime equals a times y. We transformed it to z prime equals d times z. That was a simple problem for us to solve. And then finally, we are able to say that y of t is equal to p times z of t. Because z was equal to p inverse times y. So that means that we essentially transform the problem to the basis of eigenvectors, and then the problem was simpler on the basis of eigenvectors, and then we transform the problem or the solution back to our standard basis. And so that is what's going on when we're trying to solve these linear systems using eigenvalues and eigenvectors. Is what we're doing is we're really changing the basis to a better basis for the problem.